Hello there. In this video, I am going to show you a case study of a shaft and a housing. This is a picture of the system that we're going to analyze here. If you want more details on it, click on this link here. It will take you to a paper that actually covers this particular case study, and it also takes you through a few different tolerancing approaches. So you might find that one somewhat interesting. What we're going to do here today, though, is I'm going to show you how you can use Robustica to optimize this from the perspective of minimizing cost due to failure and also tolerancing. The goals that were stated in the particular case study were that you want to maintain this clearance here, and we wish to minimize cost. Everything was originally in imperial units. I've just converted them to metric here. So if you're wondering why some things are in brackets, and if you're also wondering why some of the dimensions do look a little bit odd to start off with, that's just because of the conversion. So let's take a look at this system again. What we're really interested in here is the clearance, because as you can see, we've got some ball bearings here. If the ball bearings are too tight, then they'll wear out, or they might spin with too much friction. If it's too loose, then you probably don't have the alignment that's required for whatever the greatest system is that this is going to be used within. What we have here to calculate the clearance is this formula over here. Now what you can see is that everything is additive. And if you've read the book I've got on probabilistic design and seen any of the videos and such, you'll know that when everything is just linear and added, there's not really much room to move when it comes to robustification. So this is going to be an example of where, even though we're going to use Robustica, we're not actually going to robustify the design as such. What we're actually going to do is we're going to basically allocate tolerances in a manner that allows us to minimize overall manufacturing costs. Now this information here that you're seeing has all come from this case study here. So I'll also put a link to this in the description of the video, but also you'll be able to download this file here, so you can also click on that just to get a copy of it. You'll be able to download this file as well, just so you can I guess duplicate what I'm doing here without going through the process of setting everything up. What we've got here is, first of all, the tolerances. Now in the paper, they've assumed this model here for cost with regards to tolerances, where the cost is A plus B divided by the tolerance. And they start off with this data here. So A is essentially what it costs to set up to manufacture a part, and then the reference is the part that's dependent upon the tolerance that you specify. Sorry, B is the cost that depends upon the tolerance that you specify. This reference here is from the actual paper itself. And I've used that to work backwards to solve for B, this coefficient, which then allows us to create a formula for the cost over here. A and C and G, they don't have a reference because they're from suppliers. If I remember rightly, G and A are from, A is the circlip, and C and G are the ball bearings. So you don't really have any room to move there with those. There's no point in talking about adjusting the tolerances and stuff. You get what you're given. However, the other parts here, such as the bearing sleeve, the housing and the shaft, these are things that are made in-house, and therefore there is some control over them. And that's what these other dimensions here are. So that I've highlighted the variables that we can actually adjust. I'm assuming that these nominal dimensions for all these lengths, they're pretty much fixed because that gives us the functionality that we require. So that means this is what we can adjust here, the tolerances. Now when we adjust the tolerances, there will be a change in cost. So what we have here is basically the cost of setting up to make the parts, and this here is we've got the extra cost depending upon the tolerance that we specify. So the overall cost is this. However, you also have to worry about the cost due to failure, and that's what we're going to put into the optimization process using Robustica. That's where we're going to consider the cost of failure, and that's how we're going to look at minimizing failure due to poor quality. So this part here, this is really just setting up our reference model for the cost due to tolerance. What we have down here is the inputs and the outputs of the system. So we've got each of our key dimensions here. We've got their mean or nominal value, and we have their standard deviation. Now, this standard deviation is based on the tolerance. So you can see there's this formula here that you might not be too familiar with. And that formula is to convert a tolerance to a standard deviation assuming a uniform distribution. If you take a look at this paper, you'll see that they noted that in this context, where everything is basically machined, a good portion of the variability comes from tool wear. And tool wear is a linear phenomenon, which means we would expect that the end distribution would be uniform. So I've made the assumption that each of these input variables would have a distribution that is uniform. Now that we have the inputs specified in the output, we can put in our formula here, which is essentially just this formula over here, but referring back to the mean values of each of the inputs to calculate the clearance. What I'm going to do is use Robustica. I'm going to specify each of the inputs and the outputs, and even though we're going to get a standard deviation, because this case study works in tolerances, I'm also going to calculate the tolerance at the end. But whereas with the input distributions we assume uniform, for the output I'm going to assume a Gaussian or normal distribution. And the reason for that is because the respective formula is additive, and it is assumed that clearance will have a Gaussian or normal distribution. If you've seen my video on the central limit theorem, or if you know about the central limit theorem, you'll know that in a scenario like this, where we have random variables being added or subtracted, the end outcome is very close to a normal distribution. So that means we would expect this clearance to have a normal distribution. And typically your tolerance, your plus or minus tolerance for a variable that has a normal distribution is 3 times the standard deviation. So once we've calculated the standard deviation here, we'll multiply it by 3, and that will give us the expected tolerance. And that's where things like 99.8% of parts are within that particular range. Over here, we have the initial cost that we expect due to the tolerances, cost due to manufacture. So now that we've got that sorted out, we can look at doing the simulation. So the first thing we need to do is specify the inputs. And that is a process of going to each of the inputs, specifying the mean, specifying standard deviation, specifying the distribution we want, which is a uniform distribution, and then adding it. We now need to do that for each of the inputs. I will do that now. Specify each one as a uniform distribution. Add, we'll just double check there. Yep, everything's uniform. 18, 19, 20, 21, 22, 23, 24, 18, 19, 21, 22. It's always worth double checking that you've got the correct cells highlighted before you go off and do your calculations and simulations and optimizations. Okay, so now go back to the we'll go to the output, I should say. So the output is calculated here. We will get it to put the mean in here, and we get to put the standard deviation in here. With Robustica, this is a situation where we specify what it is that we want optimized. Now, often, if we're looking at quality, we would specify a target value. But in this context, because we're going down the path of using tolerances as our paradigm, we need to specify the maximum value that's allowable and the corresponding cost, and the same for the minimum corresponding cost. So the maximum value would be 0.51 plus 0.38. So that means the maximum allowable value, or the point where failure occurs, would be 0.89. Now, what is the cost of failure? This particular paper talks about it a bit, but doesn't go into does not go into it in too much detail. Taguchi said that failure is the cost of the customer needing to return the product and get it replaced, which ends up becoming quite a large number. If you were to be doing something like this in your own employment or for your own company, you would have to work out what you think that cost is. I am going to assume that it's about 5 times what it is to make, which I think is actually a little bit conservative, but it's also a nice round number, which just makes it a little bit easier for now. So it's 0.89. If the clearance is greater than that in millimeters, then it's going to fail and it will cost us $100. The minimum value is 0.51 minus 0.38, which is 0.13. And once again, we'll say the cost is the same, even though it might be a slightly different failing mode with bearings wearing out as opposed to having too much clearance and therefore a lack of alignment or something like that. I'm going to say ultimately we can't use the system and therefore it costs us the same amount. We now add that. So what we have now done is we've specified the inputs in the probabilistic model and we've specified the outputs, and in this case there's only one. So we can close that window down. What we can now do is do our initial moment calculation to get the mean and the standard deviation. So I'll just make this column a little bit bigger for us so you can see the plus minus in there. So we now know that that's the mean clearance that would be expected if we were to actually make this. And we can also see that that's the expected standard deviation, and I have converted that to a plus or minus tolerance, which at the moment we can see is somewhat larger than what the paper had specified. Therefore, we would expect a relatively high failure rate. I'm going to note that initial tolerance over here, and that was 0.487. Okay, that'll just be a reference for after we optimize to just check back with what changes we've seen. So now that we know where we are to start off with, we actually want to minimize the cost, and our cost comes from failure rates where anything falls out of tolerance, and also the cost of production, more so in the tolerances that we specify. And as I said from the paper, this is the model that's being assumed for the increasing cost given the specified tolerance. This is based more on machining, so if you take a look at this design, you'd probably anticipate that much of this would be machined. If you were using different manufacturing methods, you might find that formula was a bit different. This is what, as I said, this has come from the reference of this paper. You would potentially use something different depending upon the situation that you're in. So we now want to robustify. So that means we need to set up our robustification settings. The only things we can adjust here, or the only things that are worth adjusting, are the tolerances. So that's these values that I've highlighted in orange here. Everything else that I've specified so far is a part of the probabilistic calculation, but they're not input values when it comes to the optimization process. So we will specify each of these. Now, when it comes to tolerance values, I mean, usually you'd probably say something like, well, this is the best manufacturing operation we have available, and this is the tolerance it offers, and this is the cheapest, and this is the tolerance that it offers. I'm going to be a little bit more arbitrary, and I'm going to assume that we would consider something that's half the current tolerance up to something that's double the current tolerance. So we'll add that one, and the next one is here, and I'm now going to say that we've started, say, 0.2, which is a little bit less than half, and by 0.2 I meant 0.02, up to 0.1, which is double. We'll add that one. The next one will be here, and so we'll say that starts at 0.07 and can go up to 0.3. So we'll add that one, and then finally we have this one here, and once again we'll say that can be as low as 0.02 and can go as high as 0.1, and we will add that. And there is an extra cost here, and that is the cost of manufacture, so we'll put that one in there. Often when we do our robustification, we don't need to worry about these extra cost cells because we're just looking at the cost due to failure. But in this particular instance, we are actually specifically calculating the manufacturing cost, and we add that to the cost that we want to minimize in our optimization. So we've got our standard settings here: population size, crossover rate, mutation rate. Once again, if you look at the user guide for the software, that can all be explained. I'm not going to worry too much about that now. 30 minutes I've typically found is a good runtime. Usually it's more than enough. I think in this scenario here, because we do have an initial design that more or less gets the job done, we might as well include the initial values in the optimization process. I'm just going to double check these. Q6.1 to 0.4, yep, 0.02 to 0.1, yep, 0.07 to 0.3, 0.02 to 0.1, yep. Good. So that means we're now basically ready to run. So I will Robustify. Now this is set for 30 minutes. You might be interested in seeing this start off. As you can see, the original cost, if you had poor quality, was $29 and just under 50 cents. Already we have found a more cost-effective design down around the $27 mark, so that's good. We're off to a good start there. But this is going to be running for about half an hour and you don't want to watch that. So what will happen is I will pause the video and then we will come back afterwards and we'll see what we've got at the end. So we're now back and the optimization has completed. We're being presented with a question here on whether we want to accept the updated values or not. We can see that the quality loss has dropped from $29.49 down to $26.51. So there has been an improvement there. We might as well take the optimum values, otherwise there's no point in doing what we just did. And we'll see what we have. So first of all, we can see that the tolerance has dropped. But what's interesting is that the tolerance didn't drop to what we were anticipating, or what sort of the paper specified as being required. What that probably means is that given the costs of production and the cost of failure that we allocated, it was probably worth allowing a few of the components to fail instead of paying extra for the manufacturing costs. If we take a look up here, remember at the start this was around about sort of $7 or something. That's now been reduced to $5.79. What that means is that the optimization process actually thought some tolerances were worth letting out. And we can sort of do that by comparing them to the reference. Remember, the reference values were where we started. They didn't need to be where they started. They just so happened that that was what we had at that time. And we can see here that this tolerance has been tightened, which means that the cost has gone up. But this tolerance has been let out, which means the tolerance has gone down. So there are some of these components here in the design. It's actually worth loosening the tolerances and going for a cheaper manufacturing process than it is to tighten them. And also, and maybe that means that we allow some more failures, but at the same time there were other key variables that we tightened. So if we take a look here, the one that was tightened was B. So that one was tightened, and that's this dimension here. So the dimension of the shaft was an important one that needed to be tightened. And we've also see here that this one was also tightened, and that was E. So that was the housing that was tightened, and the ones that were let out was F, which is the bearing sleeve, and therefore it should also be D because it's another bearing sleeve as well, and it is. So the bearing sleeves seem to have less effect, and therefore they're worth loosening the tolerances than do E and B, which maybe was intuitive to some people watching, but maybe not to others. It certainly wasn't to me, so I found that interesting. And so there's your optimized design now. We have reduced the tolerance by making these adjustments, but we haven't tightened them up as much as what I was expecting. And that's just because it was that balance between the cost of failure and the cost of manufacturing. Now, as I said earlier, my cost of failure, I did feel I was underestimating that. It probably was a little bit higher, but it does depend upon the situation as well. So if I was to repeat this process with a higher cost of failure, or indeed if you were to download the start file, or the starting file that I've got online, and you were to go through this process yourself with a greater cost of failure, you might get different results as well. So I hope you found this particular case study on the use of Robustica specifying specifically, that's a redundant use of language, isn't it? Specifying only the tolerances as opposed to the parameters was an interesting one. And if there's anything out there that you're interested in me simulating, and you're more than happy to share, then by all means let me know about it, and I can make another video out of that. Thanks a lot.